Right. Welcome terug. So yeah, we're back. Welcome back for another lesson. So I wasn't so sure what to do. But then what came into mind is matter and material, right? So matter, we already know the definition of matter. We can say is anything that has mass and occupies space, right? Now material, it's more like matter, it's just that material now we're more in detail, right? So with matter is anything, but material we are specific. For example, wool is a material, right? The type of wool that you use determines the type of material that you used, and so on and so forth. Now I will explain to you why am I doing this now, because we'll be speaking about let's try this, the optical phenomena. Now optical phenomena, we did it in grade 11, right? Remember when we were speaking about optical illusions, right? We'll also be speaking about properties of materials, right? Properties of materials. So now, okay, we have optical phenomena, we have properties of materials. So now this is what we can do. In grade 11 we spoke about light, we spoke about electromagnetic waves. In grade 10, so in grade 11 we studied about wave nature and the wave nature of light, right? And we're familiar with your reflection, right? Your reflection, right? Your refraction, so there's something like this, right? Refraction, right? And we are also familiar with diffraction, right? So we're going to combine all of these things into one and see how we can go about doing it. So now with light, we said we have Röykg-Bev, right? We said we have the Röykg-Bev. So what this represents, this is red, right? This is orange, right? This is yellow, this is green, this is blue, this is indigo, and this is violet. So now we know that from red, or rather from, is it violet? I think it's from violet. From violet to red, the intensity or the frequency increases. The wavelength, sorry, not the intensity, but the wavelength increases. So now with a big wavelength, then you have a smaller frequency. They are inversely proportional, right? So that's basically that, what we need to understand. So we have what we call the photoelectric effect, right? Okay, good. We have what we call the photoelectric effect. The photoelectric photoelectric effect. So now, what is a photoelectric effect? Let us deal with this first. When light shines in a metal surface, right, it can eject electrons. So now this only occurs at certain frequencies. Not all frequencies apply. So now we can say the photoelectric effect is the phenomena of light of certain frequency ejecting electrons from the surface of the material, right? Now this light of certain frequency ejects electrons from the surface of the material. So that is what we call the photoelectric effect. Then now this is a phenomenon that was found by Albert Einstein, right? So now, not necessarily found by Albert Einstein, but he further clarified the meaning of photoelectric effect. He came up with the black body theory. So we're not gonna get too much on that. I want us to be as brief as possible, right? So now, Einstein's photon model of light. Then Albert Einstein used the particle model, right, to explain the photoelectric effect. So he used Max Planck's quantization of energy, right? Remember Max Planck's quantization of energy. He said energy equals to hf, right? And he said energy equals to what? Hc over amplitude. That is the quantization energy or theory. So he used that to explain that light consists of energy packets, right? We know that light has what we call quanta, right? Or quantum, right? What is quantum? Quantum is the energy pocket of light, right? So now these things called photons, right? So now each photon carries a quantum, right, or the quantum of energy, which is dependent on frequency. Now the photon propagates through the space at the speed of light, right? So now we know that the speed of light is 3 times 10 to the exponent 8. Now also we know that Planck's constant is 6.63 times 10 to the negative 34, right? Negative 34. That is that. So now, for an electron to be released from the surface of a material, energy has to be added to that material, right? That's what I want you to know. Then the added energy needs to overcome the forces that the ions of the material exert on the electron, right? Now the amount of energy is called the work function. The work function, right? Now the work function we know as work, right? O of that material. So now the work function is a property of a material. So each material has its own work function, right? So the table, we can try to tabulate the thing, but we will take more time. So Max Planck proposed that electrons radiate or absorb energies, fixed quantities or quanta. Now the energy, right, of the quanta is given in the equation, right? E equals to now let's say NHF, right? N is equivalent to 1, 0, 1, 2, etc., right? So remember the energy is given by this. So he said it radiates or absorbs energies according to the quanta. So now where H represents the constant, Planck's constant, and F is the frequency, right, of the vibration, right? So now that is what he proposed, right? So now we have what we call a photoelectron. Now we're just going through the theory. What is a photoelectron? So now a photoelectron, right? Let's first think about Einstein first. Einstein realized that a material ejects an electron, right? And if the photon of light incident on the material has an energy greater than the work function of the material, all the energies of the incident photon is absorbed. There is an absorption. The greater the energy, the greater the way the photon energy, then it gets absorbed, obviously, because we can speak about light, for example, right? Rather the sun, if it's hot, then your material, the type of material you use, gets hotter, right? I want to get to black body, so I don't want to mention color. So now, whatever the color you wear, obviously is gonna have some electrons that are absorbed due to the high intensity if the heat is too much, right? Now all the energy of the incident photon is absorbed in the process, so part of the photon's energy is used to release the electron. This is the work function, and the remainder of the work of the energy is converted into the maximum kinetic energy of the released electron. Now the ejected electron is called the photoelectron. Now photo means light. We know that electron is the negatively charged particles. So now I'm just gonna give you formulas now, but let me just state this before I give you these formulas, because I'm gonna be as brief as possible. So now a photon that has the correct energy can only eject one photoelectron. Light has a frequency that is less than the work function of a material cannot eject, and obviously there won't be enough. So now this explains why light of only certain color frequency can cause photoelectric effect, right? So now the Albert Einstein gave us this formula: E equals to the work function, right, plus your kinetic energy. Let me write it as EK. Okay, I like writing it as EK. The kinetic energy, the maximum kinetic energy of what? Of photoelectron. Photoelectron, like that. Now that is good. So now you and I can write this as what? Remember, energy here is HF, right? So now work function here is just work function. So we know that EK represents half mv squared. So we're just gonna write 1 over 2, not 1m, 1 over m. Ugh, it doesn't want to go, so I'll write 2 on top of it like that. 1 over 2 mv squared. Right, remember this is maximum velocity. So now that is what we need to understand. So now we have the cutoff frequency. Now what is a cutoff frequency? A cutoff frequency. Now with the cutoff frequency, right, remember each material has a minimum frequency. Then that minimum frequency, it's called the cutoff frequency. So this is basically the minimum frequency. So now the cutoff frequency for any material is that frequency of light which will emit photoelectrons with zero kinetic energy from the surface of the material. So there won't be any kinetic, meaning that in this case, because there's no kinetic energy, we are left with what? We are left with the work function that is equals to h and the cutoff frequency. Now the cutoff frequency will be equals to the work function divided by the Planck's constant. Now that is basically how we can narrate this factor. So now for particular material, the photoelectron HF, you can put this as your HFO equals to work function plus your kinetic energy. I like putting EK, right, max, like that. So now for the particular material, this equation reveals that the graph of the frequency plotted against the maximum kinetic energy of the photon electron is a straight line graph, right? Yeah, basically, because now, okay, you're going to have your work function, which is going to be your gradient, and your EK, which is going to be your y-intercepts, right? Now then here you have your y, this one here is going to be your y. So now let's not get more into that. Now the cutoff wavelength responds to the cutoff frequency. So obviously if it responds to that, it means the cutoff wavelength will be equal to C over FO. Remember, frequency equals to, rather, C is equals to what? Amplitude by frequency. So now this is cutoff, this is cutoff. So now the cutoff wavelength is equals to the speed of light divided by the frequency. That is basically that. So the cutoff wavelength of any material is that wavelength that of light which will emit photoelectrons with zero kinetic energy from the surface of that material. So now that is basically that. Now we have the dual nature of light. We have the particle nature and we have the wave nature. So in many instances, light behaves as a wave, right? It behaves more as a wave than as a particle nature. So now the wave nature of light can explain the phenomena of reflection, right, and refraction and interference of light. Now the photoelectric effect is experimental evidence which shows that light has particle properties, right? So now light is thus said to have dual nature, right? We said wave nature and we said particle. So it can have some fragments and it can be a wave, like, right? So now let's come up with problem solving strategies. We're going to get to an example here, right? Then after that, yeah, like that. But I didn't want to go much into calculations. Rather, let me give you the strategies and problem solving in the next video. For now, let's hold on to that. Right, to those